The next talk's about compiling effect handlers.
Hello everyone, my name is Jonathan. I'll be talking about our work to compile the effect language, which has support for effect handlers. So this is joint work with my amazing co-authors. Marius is also here at the conference and will also speak tomorrow about some other work which is related to this. So let me give you a little bit of context that motivated our work, which I present here. So a lot of our work is in the context of our programming language Effect. Effect was initially developed around 2020, and we presented it at OOPSLA back then. And well, the basic idea is that we trick imperative programmers in accidentally doing functional programming. So we want them to feel at home, but still follow good principles, right? And to do so, effect systems are very important, and Magnus already talked a little bit about that. And I think here at OOPSLA or Splash, we have heard also a lot about effect systems and why maybe sometimes you want to have them. But effect systems come with sometimes with some significant overhead and cognitive load and complexity. So we noticed that, well, if we look at a small subset of programs that have higher order functions, but not first-class functions, then we can provide users with a very concise effect system and very concise types. And we call this notion of polymorphism contextual effect polymorphism. So effect is, just to give you a brief overview of the language, is a language with the standard features of functional programming like data types and higher order functions, and also standard features of imperative languages like code data and tail calls. So code data you would typically recognize as objects and tail calls as local control flow. But also, of course, local mutable state. But what makes it a little bit unique is that we also have some other features like resources, tracking of resources via co-effects, and stack allocated regions, and for this talk, most importantly, handlers and contextual effect polymorphism, effect handlers. Sadly, I won't introduce you to effect handlers here, but let's briefly look at a very small example, right? Can somebody tell me what is the value of this free variable n in this example? Any guesses? It's not a trick question. Yes, it's actually 1. And it's good that you know that because, well, this is lexical scoping, right? This is not very surprising. And we might want to do a refactoring like this. And sometimes we do this as compiler authors, right? It's called optimizations, inlining. The question is a little bit more difficult if we look at effect handlers, or you can think of them as exception handlers for this talk here. Here we raise an exception, and the question is now, can we apply the same reasoning or not? Will this handler here be the handler for this exception or not? And the answer is not that simple because, well, in some languages like JavaScript, for instance, you could accidentally handle this exception in the higher order function map here. You could maybe even bundle a function, return it out of this try and force it on the outside somewhere. So it's not immediately clear where this exception will be handled. In our case, actually, this is what users write in our language, and under the hood, as a compilation step, we translate it to this, and this way we establish this lexical scoping again that you have seen on the slide before, right? So we can actually apply inlining to a certain degree in our language here, and users can also write this program if they want to make that intent explicit. So naming capabilities here also as a compiler technique establishes lexical scoping in our work. There's some dispute in the community whether we should call it lexical scoping, but let's go with this for this talk. So this is our work from 2020, but also other people apply very similar techniques. So there's the work by Izhou Zhang and Andrew Myers, and also Darek Bernardsky and his co-authors apply very similar notions of some form of naming of effects or lexical scoping. So we are not alone there. The question arises now, this is maybe a nice form of reasoning about effects. Let's assume this as a premise here. Now the question is, how do we implement lexical effect handlers? And we can note one thing, that originally, if you look at the literature on effect handlers, traditionally, it was very early noted that you can easily use existing control operators. There's a whole bunch, product line of control operators out there. One of them is shift 0, which was, I think, first mentioned by Olivier Danvy in some appendix. And Sam is also here today, and they noted quite early in the handlers in action paper that it's somewhat straightforward to implement effect handlers in terms of shift 0, okay? And very similarly, lexical effect handlers can be implemented quite straightforwardly using multi-prompt delimited control. This is a different kind of control, but it gives you names, so this makes the connection somewhat more clear through lexical handlers, right? If you can give names, then it might be simple or at least possible to implement lexical handlers. What's not so easy, but Dan and Ningning managed, is to implement dynamic or traditional handlers in terms of multi-prompt delimited control. There's some work on that. And our focus here in this talk is how can you implement lexical handlers in terms of shift 0. Seems a little bit like a theoretical exercise, right? So why should we ever do this? I mean, there's a perfectly valid implementation already with multi-prompt delimited control, so why bother at all? Well, shift 0, as opposed to multi-prompt delimited control, has a very nice and well-studied translation into the CPS hierarchy. And now we have seen already that we could apply this inlining trick because we have this lexical scoping, right? So we can just inline our handlers. And now let's combine these two things. We inline the handlers, then we have just a term in CPS, which is system F. And then we can apply all the existing work on optimizing system F programs and get optimizations for free without actually looking at effect handlers. How can we have effect handler specific optimizations? And that's very attractive for me because I like to import existing work instead of doing it myself again. And we conjectured in 2020 that might be possible, and we already had some good evidence about that, but we never actually finished implementing a full compiler for a language from the start to the end. And the results back then were very promising. I said, okay, we should actually spend some more time on this. So like 2 orders of magnitude speed up sometimes, right? So that was very tempting to us to work on this. So the overall goal here is we want to translate lexical effect handlers to shift 0 in order to enable the compilation to iterated continuation passing style and then perform a lot of optimizations. So let me give you a quick overview of what we want to achieve. So on the left-hand side, you can see an example with one exception, and it should be handled by the corresponding handler in blue. Right. Now we translate this, and we translate it to something along the lines of the result on the right-hand side, where we have one delimiter reset, and we have shift 0, the operator by Danvy, and it should be delimited by the reset. Right. So now if there is an additional handler in between the one that we actually want to go to, want to transfer the control flow to, well, we translate this to the following. So we still have these 2 resets that correspond to the 2 handlers, but now we need to jump over one. Okay. So this is now shift 1 in the CPS hierarchy. And the number actually, like all good computer scientists, we start by 0. And the number is like, how many resets do we need to skip in order to find the correct handler? That's the intuition. And many more. I mean, the CPS hierarchy is dynamic. There can be multiple, or the one that we use. So there can be as many resets as you want at runtime, actually. So how do we do this? How do we translate effect programs from source to iterated continuation passing style? Well, in 2020, we already performed one translation from effect, which has an effect system, to system Xi, which relies heavily on second classiness and lexical scoping. And then in PLDI22, we had a paper where we say, okay, if you have a region-based calculus, we call that a big lambda cap, you can translate that to, using CPS to system F. And both showed that, yeah, there's typability preserving and so on. So, but what was missing was this step in the middle, right? So we wanted to somehow go now from system Xi to big lambda cap, and this is what we fill in here. So if you would now compose all these titles that we had, you would end up with something like this. So today I'm presenting a typed CPS translation from effect escapabilities to regions. Right? So the part in violet is the one from today. So what's the idea here? If we slightly extend this example, we now have a local function f that closes over this capability. How do we translate this? Well, f, at the point of definition, we don't know yet exactly where f will be called, right? So in this example, actually, f will be called under one additional handler. We don't know that at the definition side. So we abstract over the distance between the definition side and the call side. Here, this offset. We sometimes also call that evidence for reasons that become obvious in a few seconds, I hope. So this is the definition side here of f, this is the call side, and then we pass this evidence, which eventually is the distance between f's definition side and its call side under additional handler. So the key insight of this talk here is that evidence, or this distance, or the offset, measures the distance between the definition side and the call side, and I will show you briefly how we come up with the correct distance here. So how do we do this? Well, this is the same example, but we just renamed the handlers to inner and outer because now they fit on the slide. So what we want to achieve is that raise actually raises to the outer handler. And we start our translation now. We start in a region. So this translation that we perform actually is a typed translation in a calculus with explicit type level regions and sub-regioning evidence, which you will see in a second. So we start in the top level region, and now we enter the first handler. And the handler not only binds the capability here, but it also introduces a fresh type level region, R outer, and evidence that everything on the top level on the outside can now be used also in this new region. Okay, this is term level evidence, and you can think of it as the number 1. So this is the current lexical region. It now changed to outer. And here we bind a mapping from the capabilities that we have in scope to the distance to how they could be used, right? So right now it's a number 0. Now we enter the inner handler, which also introduces a fresh region and evidence that now the inner handler is nested in the outer handler. And you might notice that we have adapted the translation context, so all of the existing bindings are now composed with this additional evidence that we have. We can build a transitive, we can compose them transitively, right? So before there was 0, and 0 plus R inner, F inner is F inner here in this case. And now we also entered the current region. And you can imagine, read F inner here in this case as the number 1. In CPS, actually, this is a very complicated CPS term, denotationally, but here, for you, it's the number 1. And the last question is, okay, if we are now outer race, how can we know where to go to? Well, we need evidence that R inner is nested in R outer, but we already have this evidence mapped here, and we just look it up. Okay. So evidence measures the distance between the definition side and the call side. In the more general case, if we now look at the local function f again, we see, okay, we abstract now over this evidence. F also introduces a fresh region. It's a little bit more complicated. Full details are in the paper, but you can see we pass evidence. Function abstracts over it. At the call side, we instantiate the region and pass evidence. So having implemented now finally a compiler, right, the whole pipeline, we ran benchmarks, and we were, to be honest, very happy about the benchmarks, because we could observe quite a few speedups, and these speedups are always, you can't see the next best one, always compared to the next best one. So we compared against the F language, which performs some optimizations, OOPSLA, which has very good support for exceptions in particular, and the Coca language. And we could observe speedups from 1.6 to 23 times on community-maintained benchmarks. But we could also see some slowdowns. 2 points here or 2 of these benchmarks, where we could see slowdowns, actually amount to the runtime difference of Milton, which we use to compile and run our programs, and OOPSLA. And the other one is just the reason that OOPSLA is very, very fast with respect to exceptions, and we couldn't beat that. So the takeaway is, and this is taken from the paper, this formalism evidence measures the distance between the definition side and the call side. And in the paper, we have more of these formalizations, and we have a full typed translation of a calculus with second-class capabilities into regions. We show that the translation is type and semantics preserving. We support more advanced features and also show the benchmarks, of course. And I want to insert a small plug here to another talk, because we've just seen how to go to CPS. Right? On Friday, we see how to go back to direct style. This is Marius who will give a talk on how we can define an inverse translation to the CPS translation. So in conclusion, I've showed the compiler pipeline, an example, the benchmarks, and I thank you for your attention.
Please step up to the microphones again to ask questions. Can you say a little bit about how this translation is dependent on the internals of effect, maybe even those things of effect that are kind of orthogonal to effect handling?
I think most of the features are orthogonal to the translation. So if you have name binding constructs, that's of course important because we use the lexical scoping. We do distinguish between values and computation, following the school of Paul Levy and fine-grained call by value and call by push value. We only have to do this translation for computation, actually. So capabilities, they correspond to computation. And we distinguish between these two binders. So this evidence and accounting only needs to be performed for computation. So you could add arbitrary value bindings, and you don't even need to do our translation there. But for computation, you need to do this.
Hi.
Hi, Ken.
Hi. So when the evidence is passed, it's a number, or it's evidence that a number is smaller than another number, right? But to turn that number into like a shift operation, there's some loop somewhere, right? That says, lambda n times or something. And the lambda is just skipping over the. Is that loop like a compile time on-road loop, or is there like a runtime?
It's a very good question. Easy answer is no. 0 is the identity function. 1 is a crazy CPS term that corresponds to lifting a program that runs in a scope with 1 continuation into one that has 1 additional continuation. And then composition of 2 evidence is function composition. So we can assign denotational meaning to these evidence terms. You don't need to do that to actually translate numbers into something. I just use that for presentation. In the compiler, we use CPS.
So like the loop I'm describing is sort of deforested away at like.
Yes, it's a little bit like church numbers.
Yeah.
But in CPS.
I have a maybe slightly silly question. You should be able to implement shift 0 using your effect handlers as well. I know that's not the purpose of your translation here, but have you seen what happens if you apply the translation, I don't know, twice? If you translate into shift 0 and then go back to your effect handlers and again,
No.
would you end up with a sort of explosion in the size of your generated code, or would you reach a fixed point?
Most likely explosion, I would say. I'm not sure. So it's not a reflection or something, if you get at that. No, I've not looked into that. I mean, we can talk about this.
Okay.
Sounds like a crazy thing to do.
Thank you very much.
Thank you.